Welcome back. We saw in the last lecture the use of some simple linear techniques to estimate the trajectory of a ballistic motion. And I showed you how we have used that in the past in a forensic setting to analyze the authenticity of a video. I'm going to show you one more example here to really sort of instantiate and give you some exercise in using these linear systems to formulate problems. And this one is going to be based on estimating lighting using linear systems. So let me just tell you a little story. A couple years back, when Kim Jong-il was rumored to be extremely sick and hadn't been seen in public for a while, there were rumors here in the US and abroad that he had died and that there was a body double and that there was some suspicion as to whether he was still alive or not. And in response to that, the North Korean government released this photo. And if I could just zoom in here, what you can see is what appears to be Kim Jong-il surrounded by his various military people, and they were saying, look, he's perfectly healthy, don't worry about it. And as soon as this photo came out, there was some suspicion as to whether it was real or not, and of course if it was faked, well then there would be some question as to, well, why would they fake it, and was he actually dead, and who was ruling North Korea, and so on and so forth. And so what were the things that people pointed to? Well, if you look right here on either side of this white panel, you can see a horizontal line going this way, and you can see one at the other end, but you can see right around Kim Jong-il there's no line. So why is that? Why is there that little horizontal line here? It sort of stops, and then it picks up again. That's a little weird, not clear why that is, and maybe he was spliced in and they forgot to put the line in. There have been concerns about the shadow. So if you look at the shadow of the men on either side of Kim Jong-il, you'll notice that the shadow from their leg is pretty wide, right? It's pretty thick. But look at the shadow of Kim Jong-il. That one seems to be a little bit smaller. And so it looks like that shadow is not quite the same size. And that doesn't really make sense. And so again, maybe he was digitally spliced into there. Okay, so this photo started making the rounds. Lots of questions of authenticity. And what does this have to do with linear systems? Well, it turns out that analyzing lighting can be done with linear systems. And that's what we're going to talk about today. So I'll come back to that photo at the end of this lecture, but for now, let's start just talking about lighting and illumination and see how we can model that with some pretty straightforward linear systems. So let's take this very simple scene, for example. I have a sphere that is being illuminated by some light source. Okay? And if I told you, by the way, nothing else, you could probably tell me roughly where the light is. Where is it? It's roughly somewhere up in this direction over here. Why? Well, because I've got a cast shadow over here, and I've got a bright spot over here, which means that the light is sort of shining down here. You wouldn't think that the light was over here, because then this part of the sphere would be illuminated. So you can see that there's some intuition here, just based on sort of the pattern of lightness and the pattern of shadows. And I don't think it'll surprise you, because this is what we're about to do, is I can formalize that. Okay, so I'm going to go from 3D to 2D. And the reason I'm going to do that is all the algebra works out a little bit easier. So let me spend a little bit of time in a two-dimensional world, flatland, if you will. And at the very end, just before we go to analyze the photo that we started with, I'll extend everything into 3D, and then we'll do the analysis and try to figure out if that photo was real or not. Okay, so let's go to 2D. So now I have a circle instead of a sphere. And I have some light source, which I'm going to render right up here, that little dot right there. Okay, and let me just give you a little bit of notation, because we're going to need this in a minute. I'm going to pick a point on the circle. Any point on the circle will do. I picked this one for now. And I'm going to draw a vector that points to the light source. Yeah, so there's a line right there. I'm going to call that L with a little vector on top. That is the direction to the light source. Okay. Now in this example, I've drawn the light source right here so you can see it, because I wanted you to see it. You're going to see in a minute that we're going to have to assume that that light source is at infinity, like the sun. But for now, I'm going to render it right here just so you can see what I'm referring to when I do the light direction. This right here is called the surface normal. So it is perpendicular. So if I draw a tangent to the circle here, so where is there a line that is parallel to the surface, this vector is perpendicular to that. It is called the surface normal. So the surface normal for this point is this. The surface normal here is, on this side is this. The surface normal over here is this. So as I rotate around, I become, that wasn't a very good rotation, I become perpendicular at any point tangent to the circle. So that's called the surface normal. That's the light direction. Why am I telling you this? We're going to need these two variables these two vectors rather, in order to say something about the pattern of lightness on an object given a light source. Okay, so for example here, when the light is directly above, my surface normal hasn't changed, and the light direction is now in line with that. So there's one vector that points both to the direction of the light source and is the surface normal. And obviously if the light is down here, well then you can see that the light direction is just the direction here. Surface normal hasn't changed, of course. And here, of course, you can see that this point will be in shadow. Why? Well, because the light doesn't actually strike. So if I draw a line from this point here, you can see I hit here but not here. So this is, if you will, the dark side of the moon. We don't see this part. So as long as the angle between the light direction and the surface normal is within plus or minus 90 degrees, I'm illuminating it, and otherwise I am in shadow. Okay, so let's go back to this same thing. We've got light direction, we've got surface normal. As I move the light, light direction changes, and as I move around the circle, the surface normal is perpendicular. There can be these little vectors sticking out like hairs from the circle. All right, here it is. Here's the equation that is going to tell us for a given surface normal and a given light direction, what is the pattern of illumination? So think back to that sphere. If I took that light and I started moving it around the sphere, the pattern of illumination on the sphere would change. Same is true in flatland. If I take this light and I move it down here, well then that point is going to be dark. And as I move it up here, it's going to start to illuminate, and we're going to see in a minute what happens as I move it all around the top here. So I'm going to denote the brightness at that point right there, just one point on the circle, as B. It's a scalar value. How much light is striking that point on the circle? As the following. It is equal to, what is the color of the surface? Well, of course that matters. I mean, I'm wearing a dark blue jacket right now. So some amount of light is striking me right here, and the color I perceive is dark because I'm wearing something dark. This shirt is white. So same amount of light is striking this one here, but the color is very different because the shirt is white. So obviously, the perceived appearance of this will depend on the color of the surface. Sure, that makes sense. Okay, and it's also the product of that and the dot product, notice the transpose on the surface normal, between the surface normal and the light direction. I'm going to come back to that in a minute to explain what that is. But that's, of course, a scalar value. These are column vectors, so that's a row vector, 1 by 2, times a 2 by 1. That's a 1 by 1. That's a scalar value, plus a last term over here, which is called the ambient light. Okay? So let's do this one more time to make sure we have all the variables. We know what surface normal and light direction are. That's these two vectors we've been talking about. I'm going to take the dot product of those. I'll explain in a minute why it's the dot product. The color of the surface obviously is going to multiply that. So if I'm dark, this is going to be dark, and if I'm bright, this is going to be bright. And then there's an ambient scalar term, which is just how much light is bouncing around the room. So when light illuminates a scene, so for example, here in my studio, I have a bunch of studio lights. They are illuminating me directly, but they are also bouncing off the walls, and that light indirectly comes to me, and that's what this ambient term embodies, is this indirect lighting that is the result of light bouncing around the room and just sort of giving this overall brightness to everything. Okay, so this is true under a few assumptions. Okay, assumption number one, this model. The light is infinitely far away, so let's call that the sun. Yep. It also is true assuming that this surface is a so-called Lambertian surface. Don't worry about the details of that. All it means is that it's a matte or flat surface. It is not specular or reflective, so it's not like a mirror. It's not something shiny. It's something that reflects light evenly. Okay, so that's the assumptions that we have to make. Okay, good. So what's this dot product here? Why are we taking the dot product? Well, so let's go back to the equation. So brightness is equal to the reflectance, the color of the surface, times the dot product of the surface normal and the light direction, plus the overall ambient term. All right, let me just write these things out so we can see what's happening here with the dot product. So what is n? It's a vector. Now remember, we're in 2 space. We're in flatland. So it's made up of 2 components, nx and y. So this is obviously the x-axis, this is the y-axis, and this is a vector in 2 space. The light is a vector in 2 space. It's a vector that points to some point in space. So it's that one right there. Okay, and I'm going to take the dot product of those two. And let me just remind you, the way we do the dot product is it's this times this, so nx lx plus ny times ly. It's matrix multiplication. It just happens to be a vector times a vector, a row times a column. So this component right here, this dot product, is the product of the x components of the surface normal and the light plus the product of the y component of the surface normal and the light. Okay, now where did the dot product come from? Wow, let me remind you that the dot product of two vectors, whether in two space or more, is equal to the cosine of the angle between them, that's that right there, times the length of the vector n times the length of the vector L. Okay. Now for simplicity, we can assume that these are going to be unit vectors, so we can sort of ignore that norm. And so what this is saying is that the dot product is equal or proportional to the cosine of the angle between the vectors. Okay, let's get some intuition for why that is. Look, I can just give you the model and tell you, look, this is the model assuming an infinite light source and Lambert surface, and we can move on. But it's good. We should get an intuition for this, so let me give you some intuition. So what I'm plotting here for you is the cosine and the sine function. Yeah, so blue is cosine, red is sine. So the brightness of something is proportional to, is going to be equal to how dark the surface is times the cosine of the angle. So first of all, notice that the cosine of the angle goes between 1 and -1. Okay, so that's going to be just some multiplicative factor. Now, that cosine, let's assume these are unit vectors, is equal to the angle between them. So when the angle is 0, which means that the surface normal and the light direction are aligned, then the cosine of the angle is 1. Yeah. Anything else, that term is going to go down. Okay, so let's say that I start to increase the angle. What happens is that multiplicative term starts to go down until I get to pi over 2 when I'm at 0. So let's think about that. Let's say I have the surface normal here and the light is here with an angle between them of pi over 2. Now, does that light strike this point? No, it's 90 degrees away. You remember I said that if the light is plus or minus 90 degrees, I get illuminated, and if it's less than that, I don't get illuminated. So when I'm 90 degrees away from the normal, I'm in shadow. Now something a little weird happens when I go below greater than pi over 2 and before I flip out on the other side is the value gets negative. That doesn't make any sense. I can't have negative light. So in fact, this is only true when the angle between the surface normal and the light direction is plus or minus 90 degrees because I can't have negative light. We're not going to have to worry about that later on when we do the forensic analysis, and I'll show you why. So what's happening here is that the amount of light falls off as the cosine of the angle as the light direction moves away from collinear to 90 degrees. This, by the way, right here, this graph right here and that dot product is why it's cold in the winter and warm in the summer. In the summer, like right now, the light is directly above us or close to directly above us, and so the amount of energy hitting the surface is maximal. The cosine of the angle of the surface normal of the Earth and the light direction pointing directly up is the angle between them is 0, the cosine is 1. What happens in winter is the sun is lower on the horizon, and so it strikes the surface of the Earth at a bigger angle, and so we get less energy. That's the ball game. All right, so summer is here, winter is over here. And just that difference in angle is what changes the temperature on the Earth. Okay, good. So let's go back to our equation now. So first of all, what are we trying to do? Well, if we want to analyze a bunch of people in an image, we want to know, is the lighting consistent across them? So if we go back to that image in the very beginning, I said, you know, the shadows look a little weird. That panel behind the North Korean leader looks a little weird. So is it possible that he was photographed in one lighting environment and everybody else was in another and they digitally spliced them? Well, if that's true, then the light direction for him and the light direction for everybody else, well, they may be a little bit different. And so we want to figure out for an image of an object, in this case it's a circle, eventually it'll be a sphere, and eventually it'll be a person, can we figure out where is the light given something that we know about the surface? Yeah, that's the game we're going to play. How do we estimate the light direction and then determine if that's consistent throughout the image? All right, like any good system of equations, the first thing we should do is figure out what do we know and what do we not know? And then, is our system linear? Okay, so first of all, I know the brightness. How do I know the brightness? Well, I take a picture and I measure the color or the brightness at that point. So I certainly know that. Let's assume I can compute the surface normal. So certainly if I have a surface like this, I could figure out what is the surface normal there, because I could draw a little tangent and I could draw something perpendicular. So let's assume we can measure that. Now it's going to be a little bit trickier with images of people, but we'll come back to that in a little bit. Let's assume we're going to know that as well. So I know brightness and I know the surface normal. Yeah, good. So what about these other terms? What about the surface color? Well, that seems a little harder because you need to know the surface color in the physical world. So you would need to know that my jacket here is a dark blue, my shirt is white, and my skin is, well, whatever color that is, depending on how much light I got that over the weekend. So that's probably not going to be known. See, this is known because it's in the image. This is in the three-dimensional or two-dimensional world. It's going to be a little bit harder to know that. So let's assume we don't know that. We certainly don't know the light direction. That's what we're trying to figure out. We're trying to figure out where's the light illuminating this. And we almost certainly don't know the amount of ambient light, how much light is bouncing around the room and illuminating me regardless of the directional lighting. So I've got two knowns, the brightness and the surface normal, and I've got three unknowns, okay? The surface color, the light direction, and the ambient. Okay, so the first question we want to ask ourselves is this linear in the unknowns being R, L, and A? Well, let's find out. Well, plus A, that's good. There's an additive term over there, no problem with that. N dotted with L is fine because that's just NX times LX plus NY times LY. So that's known. I'm summing up a bunch of things. That's fine. But what about this little guy right here? That's an unknown that is multiplying an unknown, and now I have trouble. And now I have trouble because that is not linear. I can multiply scalar values times unknowns, but I cannot multiply unknowns times unknown. That is nonlinear. I can't write that in matrix form. So this is not, in fact, despite its simplicity, a linear equation. Okay, so that seems like bad news. But here's the good news. I don't actually care about R. And the reason I don't care about R is all I care about is light direction. I don't care about how big this vector is. I don't actually have to estimate the vector. I just have to tell you the light is that direction. Why? The light's infinitely far away. So if I point in the sky, whether I point like this or point like this, the length of that vector is irrelevant to me. All I have to be able to do is say the sun is over there, the sun is over there, the sun is over there. And so the length of that doesn't matter, and all that R does is control the length. So if I assume that the R, the brightness on the surface, is the same everywhere, well then I can just ignore it and estimate that within an unknown scale factor. Okay, so that means, for example, if you're estimating lighting from my body, you can't use my shirt and my jacket because those are different brightnesses. But you can use all parts of this that have the same brightness. So it's a little bit of a limitation, but not too bad. But now, once we acknowledge, because the light is infinitely far away, all I care about is the direction to the light, I'm in great shape. I got a linear system. Why? Known, left-hand side of the equation, known scalar multiplying unknown, good, I can deal with that, plus an unknown. And now I have a linear system in three unknowns. What are they? Lx, Ly, that's a vector, two things, and A. I have three unknowns, and for 1 point, I have one constraint on it. I know the brightness at that point, I know the surface normal at that point, I have one constraint. All right, well, now look at, this is all the hard work. Once we've done this, now we start turning the crank. Now you know what to do. You've got one equation in three unknowns. If you want to solve this fully constrained, what do you need? Well, you need three constraints. All right, this should be pretty easy. Here's a point on the circle, here's a point on the circle, here's a point on the circle. The light is infinitely far away, so those vectors here that you see that are parallel all point to the light source. Those are the same. L doesn't change. Ambient is the same, right, because that's all the same surface and it's all in the same room. The surface normals change, N1, N2, N3, and of course, the brightness at those are going to change ever so slightly. The reflectance, the color in the world is the same, but notice that because the angle between the light and the normal, the angle between the light and the normal, light and normal are going to change, the appearance will change here. It'll be brighter here and darker here because the light is more in line with here, and it'll be maximal somewhere right around there, right, where those two line up. So I have, notice what I've done now. I've indexed the brightness at these 3 points, BI, I equal 1, 2, 3. I've indexed the surface normal, 1, 2, 3, but not the light and the ambient. Of course not. Light is exactly the same. We've already established that because the light is infinitely far away, and the ambient is the same. So now I have 3 equations and 3 unknowns. Let me just write it out so we get out of this vector notation because we're eventually going to want to write this out in matrix form. So the point for each point on the circle, b sub I is the x component of its normal times the x component of the light, plus the y component of its normal times the y component of the light, plus an ambient term. Lx, Ly, and A are unknowns. Nx, Ny, and Bi are all known. All right, I got 3 of them. Take any 3 points here. Now, obviously, we're going to want to do this for more points, but that requires an over-constrained system of linear equations. We don't know how to do that yet. We'll eventually know how to do it, but for now, let's just stick with 3 points. So 3 knowns, the brightness at those points, the surface normals at those points, and then Lx, Ly, and ambient. I'm trying to figure out where is the light, and I'm going to do this for different objects in an image and then try to figure out, is the light consistent across different objects, different individuals? Okay, good. Okay, so known, B's, N's, N's, good, that's nice. Unknowns, LX's, LY's, and ambients. Still linear, and now we can start to turn the crank now that we've set this up. Okay, so let's build the matrix form so we can solve using matrix inversion. So on the left-hand side, of course, is this vector, B1, B2, B3. There it is right there. And on the right side, we need a matrix of knowns times a vector of unknowns. Okay, so what are the unknowns? Lx, Ly, A. So we sort of know that that's going to be in the matrix. And then we've got to build everything. Oh, you know what? Let me write this out in full vector form, and then I'm going to put it into matrix form. Okay, so I've got this Lx in all 3 equations, scaling, multiplying, this vector of the x component of the 3 surface normals. So there's nx1, nx2, nx3 times the unknown Lx. Okay, I'm going to do the same thing for ny, ny1, ny2, ny3 times ly. That's the same ly. And of course, now I have the ambient. So what's the vector that multiplies? Well, it's the vector of 1. So 1, 1, 1, and then A. So known, 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 unknown A, unknown Ly, unknown Lx. What am I asking? I'm asking what is the value of A, Ly, and Lx that scales these 3 vectors so that it sums to that vector? And that's a perfectly fine question to ask. I have 3 vectors in 3 space, 1, 2, 3. I want to scale them and then sum them up to get to that vector right there. Okay, now let's put that into matrix form. So there's our generic equation written out, the dot product written out, and then we wrote that out for 3 points on the surface. All right, so now we've got our unknown vector here. We need a matrix of knowns times a vector of unknowns. We know what the unknowns are, Lx, Ly, and A. And we also know that nx, ny, and 1 are going to form the first row of the matrix, which then multiplies that unknown Lx, Ly, A. So let's make sure we've got that right. B1 is equal to, let's do the first part of the matrix multiplication. nx1, Lx, plus ny1, Ly, plus A. Lx, nx1, Ly, ny1, A. So that's the first row of that, of this system, which is one of these equations right here. And now I can do the next row and the next row, putting in the surface normals from the second and the third. Okay, what do I have? Known vector, known matrix, unknown vector. This is a what? 3 by 3 matrix. I can invert it, assuming that I didn't pick the same points and the surface normals are exactly the same. All right, so I've got a matrix B, a vector B times a matrix N, capital N, times an unknown vector U. That's 3 by 3. I simply multiply left and multiply by the inverse of that matrix. N inverse B is equal to N inverse times N times U. N inverse times N, of course, is the identity. And I've now solved for my unknown, which is N inverse B. Now, what is my unknown? It's equal to Lx, Ly, A. I don't really care about the ambient term right now, so let's just drop that off. I've estimated the direction to the light source. I just take the first 2 components of that vector, and I'm done. Okay, good. All right, so that whole thing was in 2D. Yeah, we had a flat land, we had a circle. In the same plane as that circle was some light. I could move it around like this, but I can't move it up and down out of the plane. But it turns out, and the equation was just linear, that with certain assumptions of Lambertian surface infinitely far away and the same appearance of that object around the parts that I'm analyzing, I could write that the appearance is equal to the dot product between the surface normal and the light direction plus an ambient term. We wrote that out, 3 equations, 3 unknowns. By the way, notice that it's a 2-dimensional problem, but I had 3 unknowns. Why is that? Well, the light direction only had 2 unknowns, Lx, Ly, but I had to have that ambient term because that's the reality of the physical world, is that there is this ambient term. So to go to 3D, let's think about what we need. Well, we're going to have 3D surface normals, a 3D light, and still an ambient term. So we're going to have 4 unknowns we're going to have to deal with. Now, a couple of things we're going to have to do. We're going to have to sort of reformulate everything in 3D. Hopefully that won't be too bad. And then I'm going to show you the application of that to the analysis of Kim Jong-il's images. All right, so when we come back, we'll do this whole thing in 3D and figure out if that image was real or not. See you in a few minutes.